All right, so the last concept in section 4.3, and this is video number 3, and this will finish us off for 4.3. The last concept is the factor theorem. And the factor theorem, and actually I'm going to throw some extra little tidbits in here, so not all of this really belongs to the factor theorem, but I'm going to throw some other things in here that we know as well. But the following statements are equivalent. That means if we know that one of them is true, then automatically all of them are true. So some things that we've already learned. If we plug a number into a polynomial and we get back 0, one thing I know about that is that a is a 0 of the polynomial. That's just straightforward definition of a 0, and we've seen that before. And something we've already also talked about is that the point A0 will be an x-intercept on the graph of that polynomial. So the new ones that come with the factor theorem are that if we take p of x and we divide it by x minus a, and this is the exact same a that we're seeing in number 1, 2, and 3. Whenever we take that number and we write it as a factor, it's always x minus the 0. So p of x divided by x minus a has a remainder, and you might be able to guess this if you've been following along. Remember, the functional value also tells us the remainder. That was our remainder theorem. So it has a remainder of 0. And when we divide and get a remainder of 0, that means that these two expressions have a special relationship. That means that x minus a is a factor of p of x. So really, these last two pieces are what the factor theorem tells us. If we can divide and get a remainder of 0, then x minus a is a factor. And remember, dividing by x minus a would be the same thing as finding the functional value at a. And that's pulling the remainder theorem in as well. So we can do a bunch of checking to see if some particular linear expression is a factor of a polynomial just by dividing and seeing if we get back a remainder of 0. So I want to do a few examples. This will also give us some more practice with our synthetic division, and it will help us because in section 4 we're going to start taking these very large polynomials and we're going to be factoring them down into linear pieces, and we're not going to have any clue on how to do this by hand. We've really only learned in algebra classes before this how to do quadratics, and then how to do larger polynomials if we can do factor by grouping or if we can pull out a common factor. Now the polynomials we're going to see in the next chapter, none of those rules are going to apply. So we really need this factor theorem to help us out in figuring out which are factors and which are not. So we're going to determine if each is a factor of f of x equals x to the 4th plus 9x squared minus 10. And we're going to use that same polynomial and do a few examples. And the first one we're going to try, let's say, is x minus 2. Is x minus 2 a factor of that? So we can't really just look at it and tell, but we've got all these rules up here that if we can figure out any one of those, then we can automatically say that all the other ones have to be true. And one of those is that deciding something is a factor. Well, if I can show that dividing gives me a remainder of 0, or that it's an x-intercept, or that plugging it in equals 0, then the answer is yes. If it's equal to anything else, the answer is no. So I'm going to do synthetic division to give us more practice with that. For a lot of you, this might be the first time you've seen right now in this class might be the first time you've seen synthetic division. So it's really important throughout this chapter. So remember, when we set up synthetic division, we take our factor and set it equal to 0. So we're really going to be using 2, positive 2, in the box. And notice up here in our rules, A is positive, A is positive, A is positive. But as soon as we start writing it in a factor, it's x minus A, x minus A. So when you see it written in a factor and you want to pull it out to use it, you change the sign. So if it's x minus 2 in the factor, it's going to be positive 2 that we use in our synthetic division. And next to it, we're going to write out our coefficients. This is a 4th degree polynomial, so we should have 5 coefficients. And x to the 4th has a coefficient of 1. And work your way down. X cubed is missing. That means coefficient of 0. X squared has a coefficient of 9. X, just our linear x term, is missing, so coefficient of 0. And then our constant is negative 10. Don't forget to bring those signs with them. So the positives don't need pluses in front, but the minuses do need to bring down negatives. And the rule for synthetic division, first one always comes straight down. After that, we're going to multiply, and then we're going to add. So multiply, add, multiply, add, multiply, add. And the last number is the remainder. That remainder is not 0, so x minus 2 is not a factor. Quick way to decide. So I'm going to use this exact same polynomial, and I'm going to check another one. Hopefully we'll find one that works. So we're still working with f of x equals x to the 4th plus 9x squared minus 10. And this time I'm going to check x minus 1. So opposite sign goes in the box, so a positive one. And we're using that same list of 5 coefficients, 1, 0, 9, 0, negative 10. First number comes straight down. After that, we're going to multiply and add, multiply, add, multiply, add. So 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 9 plus 1 is 10. 10 times 1 is 10. 0 plus 10 is 10. 10 times 1 is 10. Negative 10 and positive 10 is 0. Last number is the remainder. We love this. This is helpful, especially when we go on to chapter 4 next week. Because the remainder is 0, it means x minus 1 divides f of x perfectly. And x minus 1 is a factor. Yes, yes, yes. Awesome. Let's check one more. Let's check x plus 1. So I'm going to pull the opposite sign of that out, and I'm going to be checking negative 1. This is the number I'm going to use to help me multiply every time. Same coefficients right now. 1, 0, 9, 0, negative 10. I want to know if x plus 1 is a factor for this polynomial. First number straight down, and then we multiply, add, multiply, add, multiply, add, multiply, add. We found another one. Awesome. We have found 2 factors for this polynomial. X plus 1 is also a factor. So even though you may look at this and say, oh my gosh, it's got a power of 4, I don't know how to factor it, we could check different linear expressions to see if they're factors. And in section 4, for next week, we're going to come up with a way to pick some smart choices here so that we're not just going willy-nilly checking everything. There are some specific patterns that we'll always see in these factors based on what that original polynomial looks like. For right now, though, I'm giving you the original polynomial, I'm giving you the factor, and I'm just asking yes or no. So if remainder equals anything but 0, no, it's not a factor. Remainder equals 0, yes, it is a factor. And this is what our factor theorem tells us.